And then the week after that, Scott is going to give one on sheets through history. It's pretty exciting. And then, of course, I blank. Nick Chura, who's not here, he had to take care of something this afternoon, is doing something on origami. And it's not just origami, it's how to do math with origami. That's just weird to me. So, tic-tac-toe, no, it's Connect Four. And then we'll be done with spring term and off to summer. But James was a student of mine. We met a couple of years ago. And then he came by once like, hey, I have this idea for a dead math talk. And I was like, yeah, I'll look into it. And I put a little pin in it. It's on my bulletin board still. And then he came to me later. He's like, what the heck, John? Not really. He came to me with this idea. And I was like, wow, let's do it. Let's just dive in and see how it goes. Because I don't even know how to advertise it. It seems to me like you were inspired by something in your chemistry class. And then Pandora's box opened. So, James Perrin, thanks so much, and enjoy.
All right. Wow. Thank everyone so much for coming. Let's see. How should I even start the meat and potatoes of this? So basically, how I want to go through this is just kind of go through. I have like a very non-traditional mathematics background before starting to attend here like 3 years ago. So I have I don't even know what to call it, like brute force method of figuring things out initially. And so I think a lot of it's like probably from like having to like fix guitars and TVs and stuff like when I was younger. And so it's kind of just like, well, it's not working, try moving this, try wiggling this, try banging on it. And that's kind of what I did with this. So I'm gonna walk you through what that was like, and then I'm gonna try to like do my best like at attacking it from a more formal perspective. And I've got cue cards for that in case I forget something. So every time you see me look at one of those, I'm forgetting something. But for now, I guess I'll just start off. Let's see. So I was thinking a lot the past year about just like ideas of how you could kind of break down information in general. I was thinking of things like, I don't know, the cosmic background radiation, whatever, just the idea of something that has some sort of wave pattern to it. And I wanted to think of, I'm like, well, what are the tools I have for that? The only tools I had for that at the time, it's like, I know I can like integrate things, I can differentiate things. What's like a good way we could approach it with that? And I'm like, well, the more I thought about it, the more I realized, okay, this wouldn't really make sense because an oscillating function, it just keeps going. You can just keep differentiating, it's just going to go in a circle. And so I'm like, well, this might not work. And then one day I'm in OChem, and my professor's talking about the NMR machine, and she said, well, how the NMR machine works is you've got, I guess, this is a crude proton. And how it basically works is if you induce a magnetic field and you have some sort of substance in there, and if what you're aiming for is, say, hydrogen, what you need, you can't use elements that have an even number or an even mass number because they'll basically cancel each other out. And so you need, well, actually, no, that's not right. They don't have spin. You need something with spin, and spin is this idea that a proton or an electron or anything else can have this spin. And what the spin does is it's like, if you imagine me like throwing a baseball at you, if there's no wind and I don't, throw it like in a silly way, ideally it'll go straight. Spin's kind of this phenomenon that we know of that basically says that even though these things aren't spinning, they act like they're spinning. So if you've seen someone throw a beach ball like, woo, and they throw it straight up and it starts curling backwards and it falls behind them, it's kind of the idea that protons do that when they have an odd mass number. They have a spin of 1/2. And so even though they're not spinning, they act like they're spinning. And so you get this thing called precession. So if we knock it over temporarily using like RF, it goes down or it flips to the higher energy state, and then on the way back up, it kind of creates this like it processes. So it's like if you imagine like holding a gyroscope down, if you had like, I don't know, a motorized gyroscope, if you held it down and then let go of it, it would work its way back up to spinning again. You push back down and it would manage to keep coming up. And so the idea with this NMR machine is it's basically measuring the fact that protons, if they were all in the same environment, they would process at the same rate and we wouldn't get any useful information. So the fact that they're kind of surrounded by different chemical environments, different electrochemical environments, it causes shielding, so they experience this net magnetic thing in different ways, and that can be captured by putting in let's see if I can draw this. It's kind of like, if I try to pretend it's on a 3D thing for a second, it tries to, you can measure it on the transverse axis, and so when you first hit it with the RF, they like all obey, you have a bunch go down, but slightly more will go up because the higher energy state would be spin down. And so spin up, it's the lower energy state, you have slightly more because of thermodynamics and stuff. In that state, so you have a net magnetization vector that's pointing up. And let's see if I can achieve this. And so when they both go, if you have like half of them going up, a little less than half going down, they're all still spinning, mind you, but if we kind of like lock in our axis to their spin, then we just kind of see that the net magnetization vector in that moment is going to point to the right. The reason for that is because if we have some going up like this, some going down like this, and they're processing, of course, then what happens if we add these together? So that one, tail to tail. Oh, look at that, pointing to the right. So we end up with it there, and then as they fall out of sync, it works its way back up, but it, of course, spins like that on the way up. And so we can measure that. It's called the free induction decay. i.e. looks something like this. And it decays. And so that is what they get. That's what the machine reads, and it uses some sort of mathematic operation to turn that into something useful, into something that tells us the environments these are all in. It tells us, we can figure out what elements we're dealing with. And so I'm like, this sounds like this is it. Okay, like this sounds like something that you can take a wave and turn it into useful information. And so, I jumped right into it. And one of the first things that I found out about this, I'm going to give you another eraser. The very first thing that I saw was the Fourier Transformation. So the Fourier Transformation, I'm not going to go over it yet, but I guess there's a couple different ways you can write it. I'm going to use like the more quantum notation. That's just kind of like f of x of psi of x. Remember it. And there's like several different ways people do it. Some people do for different reasons and for different applications. You're going to have varying or no coefficient out front like this. Then you're going to have your function. Let's see. Actually, I'm doing this backwards. This seems to be k. Sometimes ikx to pi, a couple of different versions depending on whether or not you want the frequency in different terms. And so when I first see this, I'm like, okay, like this is great. Like I can just take a wave function, I can just plug it in, it's going to spit out magic numbers, awesome. Like this is going to be so easy. This is going to be so easy. And so I plug it into my calculator. I think I just finished doing that actually. I pop it into the calculator. And to my dismay, I get all these terms. I'm like, well, this doesn't look very useful at all. Like, I don't know what any of this is. Like, I don't know how to do this, apparently. And so I got 1 term, 2 term, 3 term. I don't know what's going on over here. 4 term, 5 term. Oh, and then it's a complex number to boot. I don't even know what that is at that point in time. I'm like, But then I kind of thought about it. I reasoned my way through it. I'm like, okay, I've got a real part and an imaginary part. The imaginary part is always just going to have this coefficient I on it. And so I can isolate the real part by just separating it. So I'm like, okay, if I just pretend the imaginary part isn't there, like, maybe I can like Desmos it or something. So then that's the next thing I tried. Let's see if I can pull up the Desmos. Let's see. First thing on this one. Not that one. That looks good. Okay. So pull it into Desmos. I'm like, great, a flat line. This is exactly what I wanted. This is it. This is the meaning right here. So no, that didn't work. And then I did some tinkering. I'm like, okay, maybe if I turn one of these variables into a slider, maybe something will happen. And so this is just one of those terms, in case you're wondering. So I think I got 4 real, 4 imaginary. Since I plugged in a function, I just wanted to test it, so I plugged in cosine 4 pi x plus cosine 6 pi s. And I'm like, okay, tell me the frequencies. I'm hoping to get, what am I hoping to get back? Cosine 4 pi, that should be how many oscillations is that? What's the hertz on that? Do I have it on here? Do I have something on here? At cosine 6 pi s. Okay, so that looks like 1, 2, 3, cosine 6s. So cosine 4 pi x, I was expecting to get 2, I didn't. And so I put the slider on it. I'm like crossing my fingers here. Oh, what's this? The slider magically starts making this peak. I have no idea why at this point in time. And so I'm like, okay, it looks like something's working. And so since I did cosine, the full thing had both peaks. Let's see if I can switch to that one. There we go. And so I was like, awesome. Like, this is incredible. I don't know how this is working. I want to know how this is working. And so I realized that by putting a slider on increasing the frequency towards infinity, essentially, if you wanted, it's creating these peaks that are just going higher and higher and higher and higher. And they'll just go all day, get skinnier and skinnier and go up to wherever. And it's at my frequencies that I'm looking for. I wanted to take this and I wanted to see, I knew that by adding cosine 2 pi or 4 pi x and let's see, do I have that on here? I might have that on here. I knew that by adding them together, this is a bunch of garbage. Can I add an item? I knew that by getting this wave, which it seems kind of counterintuitive at first. You're supposed to be using like a random wave that you don't know the function. So in this case, I'm kind of reverse engineering the thing. But I knew that it was a good way to test it, and so let's see, 2 pi x plus cosine 4 pi x. Yeah, so I knew that what I was putting in was something like that. Maybe if you looked at that, you could be like, oh, that looks like cosine 2 pi x plus cosine 4 pi x. I don't need the Fourier transform to figure that out. But the idea is if you add a bunch of them together, it's going to get real wonky real quick. If you want to like make it even more complicated, you could just add whatever you want onto it. Try to make it more difficult. Yeah, let's see someone figure that out. What's the frequency there? And so I'm like, okay, I got that part figured out, but I wanted to to understand like how am I supposed to use this? And so I started going down the rabbit hole of all that stuff. But along the way, let's see. Can I use my keys to do this? No. Okay. That would have been useful 5 minutes ago. That would have been useful 10 minutes ago. Oh yeah, I guess. So on Joseph Fourier, the person who figured this thing out, I thought it was really cool to hear that it's like Fourier wasn't just some like, no offense, Darwin, but it wasn't like one of those Darwin people who just come from like, you know, this wealthy background and get pushed through all the academics and stuff. Apparently, both of Fourier's parents died by the age of 9, I'm pretty sure. And so he was an orphan and actually, you know, put himself through school and just strove and, you know, did all these things. By like 20, I think he was like saying, he's like, oh, I'm still not as good as Newton and these other people, like I need to get going. But apparently Napoleon thought he was like a genius, and he's like, no, we can't have you at this academy. You need to like come be the governor of this place. He knew that he thought he had him in the pocket, I guess, and wanted to use him to push some agendas or something. But I really think that, you know, it's cool whenever you see people that come from these backgrounds against all adversity and look at what they do with it. It's awesome. But let's see. The meat and potatoes of this. The meat and potatoes. So, a couple of things. Should I go to the next one? No, not yet. A couple of things. So this is here. So one of the ways that's a lot easier than having to do this, especially not by hand, because after I did that on my calculator, I'm like, awesome, I want to make sure I can do this by hand. That was not a great idea. It turned into this, and that went on for a while, and it kept going on for a while, and it kept going on for a while, and I'm like, okay, so cosine and sine, not the greatest thing to have to deal with. You almost always run into recursive integration, which is just, you have to just, I think you call it the Bunsen over the Johnson, and it's basically like that. But I guess if you just replace with, if you put in the function when you end up getting in your output something that you saw, that you started with, then yeah, you can replace it with I, and then you can substitute blah blah. But it goes on, it goes on, it goes on, and I kept forgetting minus symbols and all kinds of parentheses and stuff, and I'm like, this is really hard, and I eventually got it, but I was like, there's got to be an easier way. And so it turns out how people actually do this is they use something called the Dirac delta function, which is, I'm using the fancy chalk. The Dirac delta function. So I'm like, awesome, like another tool that I can use to understand this thing. What does it look like? Try to put that into Desmos, it doesn't work. It turns out you can't, a distribution isn't a legal function. And so what that actually looks like is it's a point, nearly infinitely thin, I don't know, goes up for infinity, at 0 when it's written like this. And so if you want like a definition of it, I think what they do is they say that the integral of delta x with respect to x equals 1. So weirdly enough, the area under this infinitely tall and infinitely thin point going up, by definition, the area under that is 1. And I'm like, okay, that I don't feel super comfortable with that, but you know, we can get this to work. Another useful thing they say about this is we know that if we take the delta function, let's see, x minus a, and then some other function, I don't know, like sine or something, but we'll just say x. going to give us that function. Let's say it looks something like a sine. Let's say that a is over here somewhere. And so the delta function is going to give us this point. Same deal, super infinitely thin thing, only now it's giving us a way to represent that exact spot on this function when we mix them together like this, when we multiply them together inside the integral. So it's a useful property, I guess, because anywhere else outside of this, if we evaluate it anywhere else but that spot, this is just going to be 0, that's going to be 0, and only there at a are we going to get the output of the function that we multiplied the delta function by. And I'm like, okay. I'm like, how does this help me not have to do 3 or 4 pages of this crazy, integration with these waves? Like, how could, like, how do I get this done? And so, let's see. So where the Fourier transformation comes from is a Fourier series. And a Fourier series, if I had known this before, I would have done this probably on Fourier series and then done the next one on Fourier transformation, but there's just going to be a whole lot of hand waving tonight. A whole lot of it. So let's see, the Fourier series, let's see, it's take a wave function, so it could be anything, could be as simple as a sine wave, could be super complicated, but the idea is we have some sort of wave function, and we want to expand this wave function. So we want to use some number of sine and cosines to build this function, which that's a super important part of a Fourier series, is this idea that we can recreate any wave using a sum of cosine or sine. Pick your poison, whatever. So if you have some crazy arbitrary wave function that says that, actually I think the example they really like to use is this really silly function that's just, I think it's something like that. It's like a step function. Like, doesn't even really look like a sine function. It argues that even with something like this, if we solve for this, so I think there's a little bit more to this. There it is. Sum. First part. Yep. So it's a sum, and what we're going to do is if we solve for these coefficients actually turn out to be pretty crazy themselves. It's something like turns into some crazy thing itself, and then if you solve for these coefficients, what these coefficients are is they're weights. So they say, with sine or cosine, a really broad one or a really skinny one, it's going to like some more than others. It's going to say this number is going to reflect the fact that there's more of that particular sine or cosine in this. And so, if you're starting out with certain bigger cosines or little cosines, when you start adding them all together, like slowly but surely, you're going to get some wave function. It's going to go up, and then it's going to be like this. It's going to go up, And the more terms you put in there, the more that this thing that kind of starts out looking like a, pretty basic summation of waves, and it's going to just start resembling that shape more and more and more. And so that's basically what the Fourier series does, and that's, the major inspiration behind the Fourier transformation is we can derive the Fourier transformation from the Fourier series. And so, in an effort to do that, let's see, what's the first thing we can do? The first thing we can do is there's something called Euler's identity or Euler's formula. And this is kind of like the first key piece of avoiding having to deal with these massive amount of sine and cosine, is this idea that E the Ix equals cosine x plus sine x. And there's an I in there. There's that I again. E to the Ix equals cosine x plus I sine x. And so this is actually pretty useful, because what this does is, and I don't want to just hand wave this. So what this ultimately ends up looking like is, when you have cosine x plus sine x, what is it going to look like? If we evaluate it at different points, it's going to draw us out something like a parametric kind of deal, right? Just going to go around. And so e to the Ix, it's the same thing basically. So e to the I times pi is going to evaluate over here. E to the I pi over 2. E to the I negative pi over 2. And then everything in between, it's going to have the same behavior as cosine sine x, cosine plus sine x. And the reason we're putting that I in there in this case is because this isn't necessarily the Cartesian plane, this is the real imaginary plane. This is the imaginary plane. And so when we end up doing certain values, we're going to end up somewhere on the real axis, somewhere on the imaginary axis. And the reason this is important is because this is going to allow us to rewrite this a little bit. So what I'm going to do is I'm going to turn n over r. This is going to move away. N over r equals k. So I'm changing that so I can consolidate that for a second. Let's see. Equals psi of x equals the sum of this new thing that we now have, which we can use to express this, but as this complex exponential thing. And so exponentials are evidently a lot easier to deal with. And so, make sure I didn't mess that up. Exponential, yn, one caveat. And there's going to be psi sub n. And so what this forms, and this is a painful thing to have to do, but I do have to waive some of this. So this psi sub n times e to the ikx is forming a basis. And so a basis in quantum mechanics is kind of this complicated thing that it's made up of an eigennumber and an eigenvector. And all that's really saying is that we got this plane. So let's say we have some sort of gridded thing. So we got a vector. Let's say it's like this. Let's say our basis goes there. And if we want to transform this, let's say we transform it up one and over. let's say we just stretch all these grids over and see what it does to these vectors. It's going to stretch this by some amount. It's going to stretch that. So these two are now here. If we'd started with some vector in between the two, it's going to get stretched somewhere away from where it was in terms of degrees. But we notice that this one just kind of gets scaled. And so there's significance to the fact that those are just getting scaled, because those turn out to be something called eigenvectors. And so there's this thing that we can scale it and descale it, and it basically lets us represent certain wave functions in this unique way. And so that's about as far as I can go with it for now, but it might make more sense in a minute. So we know we have a wave function. We're taking a sum of an exponential that was previously this sum of these cosine functions. And so now we have to, let's see, what else can we do here? We want to isolate the coefficients. So these coefficients are now the psi sub n thing. And so we want to get the psi sub n thing by itself. How can we even start to achieve that? So there's some weird little fancy tricks we have. We can do I to the negative I m x. M is just some random integer, we'll say. Over R. Let's see. I need to turn this k back into that and over R. And so the property of exponentials is that we can slap those together so that they become, we can turn this into n minus n over. And then the next thing we can do is we can integrate both sides over a range of 2 pi. 2 pi is nice because it keeps things, we're integrating over a fixed amount of periods. So let's see, we run this idea. So now we've just done these seemingly arbitrary things to both sides. It's like, well, how's this going to help? So if we look at what we're integrating on this side, we know that this exponential is going to be some combination of cosine and sine. We know that if we integrate over whole periods, very generic function. If we integrate something like any sort of periodic function like this, you're going to get 0, right? So for any number of periods of this thing, for any of these cosines and sines that we're messing with, we're going to integrate it, and at any point we're going to end up, it's going to integrate to 0. So for as far as our sum is concerned, we're just adding a bunch of zeros, except at one point. And that point is when n equals m, because when n equals m, we're going to have a 0, and when there's a 0 up there, what's e going to solve to? it's gonna turn into e to the 0, which is 1. We're gonna integrate it, and we're gonna, fundamental theorem of calculus right here, we're gonna get pi r minus negative pi r. We're gonna get 2 pi r. And so, let's see, at that point, if I solve all of that, we're gonna be left with some weird quantum basis thing that will eventually be unified. And let's see. Not getting anything. It's gonna get weird because since we have this k going on, and the k is n for r. And then, oh, because that's right. Since the summation, since I'm doing the sum, and we know that based on, kind of do like a little piecewise kind of deal, we know that 0, it's going to be 0 when n doesn't equal m. It's going to be 2 power when n does equal m. And so, when we sum that all, we're going to end up just getting 2 pi r plus 0 plus 0 plus 0. And so we can say, okay, now, what do we want to isolate? So, since my goal initially was to isolate this, I'm drawing so big. Coefficient divided by 2 pi r, so 1 over 2 pi r. Since we decided that n, in this case, n equals m, a random integer doesn't really matter anymore, so let's turn that back into n. Okay, so then equals 1 over 2 pi r. Okay, and I think at this point, I can fix this into something that makes more sense. So psi sub n, actually this one, so instead of doing n over r, I'm going to turn it back into k, we can have there. Let's turn this into psi sub k, and I can turn psi sub k into, if I want to turn psi sub k back into something that makes a lot more sense as far as traditional functions, so like, let's see, a momentum space wave function, so psi k. There's some conventions that come along with it, and I'm just gonna have to r 1 over square root of 2 pi r is going to allow me to go away from my strange psi sub k back into something that makes sense. This actual function, psi of k 1 over the square root of 2 pi r. The explanation as for how I can justify the y sub k can make this jump, I can't thoroughly explain at this point in time, but I will try to in a minute if I end up having time. So this is okay. If I sine k 1 over 2 pi r, so if I move this to this side, because that's going to be right here, move it to this side, it's going to end up top here. And then the r's are going to cancel, multiply top and bottom by the square root of 2 pi, and we're going to end up with 1 over 2 pi, which is looking a little bit closer to what I want to see. So that's good. At that point, what am I missing? Oh, I'm missing this. With respect to, oh, that could have been justified too. But am I missing anything else? So you'll notice that this is a little different than my psi of k, and that's because this is the inverse Fourier transformation. And so the inverse Fourier transformation looks exactly like Fourier transformation, except it's got negative in front of that imaginary number. So e to the negative I k x psi of x with respect to k. And so to get the normal Fourier, I'm going to have to jump back to this equation before I started messing with it too much. Psi k psi e So doing a very similar thing, this function, when we take the limit of r to infinity, you probably remember, potentially depending, that in the case of the definition of the integral, when we take the limit to try to get our Riemann sum-esque proof of the integral, when we take r to infinity, in the case of the sum, we can transform it. So that you're starting with psi of x, which is going to be our time domain function. So this is going to be like if you had an MP3, there's your song in waveform that shows up in iTunes or something. And then integral.
James, did you say that's an iTunes song? Is that how there's
So the psi of x, like a weird property of the Fourier Transformation is the fact that you're going to put in an f of x, and you're going to be going between f of x, squiggly Fourier, and then you're going to end up in frequency land, or if you're dealing with space, you're going to be going from something that's representing a point in space, and you're going to end up going to the frequency or momentum realm of things. And so like a really useful thing people are going to do with this is they're going to, like, if you were doing like sonar or something and you're like, okay, like let's send out a bunch of waves and try to figure out if there's anything in front of us. If you start putting out really short pulsed waves, it's going to tell you a lot more information about like where it is. And so you're going to, like, if there is something in front of you, you want to know where it is, or do you want to know what it's made of? And so if you want to know what it's made of, you put out like a long pulse. You'd be like, ooh, and it's going to come back and it's going to be duller or higher. And that's going to tell you, oh, it's like a whale in front of us, or oh, it's a giant boulder. If you send out a bunch of pulses, it's going to be more useful for saying you're getting back like a tick, 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 tick. It's going to tell you that whether there's multiple things out there in front of you, and that'll be more useful to you. And so when you're going from the space-time domain, you're trying to get back information about the frequency or the momentum domain. Or you could do the opposite by using the inverse Fourier transformation. And so it seems like you'd be able to do like this perfect thing where you could, have all the information possible about both, but you can't, because there's another thing called the Heisenberg uncertainty principle. Delta P, that's momentum, delta X, that's position, equals constant. Planck's constant, right? So delta P times delta X is equal to Planck's constant over 2. And so all this really tells us is the more certainty we know about momentum, the less we can know about X. And the more certainty we know about something's position, the less we know about momentum. And so I think I actually have something that can reflect that. Where are you? Desmos? Where have you gone? Oh. And so you can see when you're like messing with plugging waves into this thing, if you plug in something that has a certain characteristic to it, let's see, where is it? This is like a really classic thing they'll do. They'll say, okay, so if we pretend that little box is like what we know about something's position, the position of a particle in quantum mechanics is given by a wave function. So it's like, okay, so if we're this certain about a particle, if we take this function and take the absolute value and square it, it'll give us like a probability of finding that particle here or over here. And so the more we know about exactly where it is. So if we say, okay, let's be really certain about where it is, we now know not very much about its momentum, right? Because this other function that you see growing, that's what we know about its momentum. So if we know a lot about its momentum, and you might recognize this as the sine c function. The sine c function is one of the interesting ways that they've gone about proving that the Dirac delta is kind of useful for getting answers out of the Fourier transformation. But yeah, if we have a lot of information about the momentum, we have very little information about its position, we have a lot of information about the opposite, the opposite is true, and so what's going to happen now is, let's see, the final thing after we end up, the whole point of even explaining the Dirac delta function, and so this actually kind of makes a good point, that instead of solving this, what is it, cosine, blah, blah, blah. So, like I initially had in my calculator, 4 pi x cosine 6 pi, actually, let's do cosine. We're like, okay, Fourier transform this. I'm just going to use ikx 2 pi. When we're solving this, we're going to realize that, like when I had in my calculator and when I had a Desmos and you saw that thing just growing in the middle, that's very symbolically similar to what you see here, which is the sine c function, which is something they use to kind of prove that the Dirac delta that we saw earlier, which is that thing that just shoots up. It's not a legal function. The sine c function kind of emulates that behavior. And if we take a constant within the sine c function and take it to the limit, it starts really behaving like the Dirac delta. And so that's kind of why it worked the way that it did in the thing that I was messing with earlier. So this cosine 4 pi times x e to the negative I kx 2 pi. So using Euler's identity again, we can turn this into, oh boy, let's see. Believe it or not, this is that. I just rewrote it as exponentials. Major hand waving. Okay. If we start solving this using exponentials now, instead of trying to do it with cosines and ending up with like that nightmare that I had earlier, it turns out that when we finish solving this, you know, what ends up happening is this same thing as before, property of exponentials. We add them together. You add together the exponentials due to the fact that when we multiply exponentials, we have that property that I kind of showed earlier. E to the, this is going to look something like e to the negative I to pi k minus 2 plus e to the negative I pi 2 k plus 2. You're going to get something like that. And this is only useful because the Dirac delta, as that we can prove with the sine c function, which I'm also going to have to, say, interestingly enough, the delta function can be defined as a Fourier transformation e to the negative ikx. Respect x. How many more times can I forget that so it becomes this convenient container. The direct delta lets us express the fact that what's going on with these when we take the limit and sort of do that same behavior that I did earlier when I had no idea what I was doing, and I'm shoving it together, and it's like creating this column that's going up. With this specific case, with cosines, you can't do this with discrete functions that are like, if we're not just dealing with a perfect cosine, if we're dealing with something in nature like the NMR earlier, we're going to end up with direct delta, and it's going to have these, and it's just going to solo it out, and you can kind of see that it's like, okay, this is this container that we're representing with the direct delta function, and now inside that container, we can minus 2. And we're going to have the 2 down here, and that's because when we're solving this, we're going to end up getting a 1 over 2, and that'll just come outside of the integral. This is the way easier way to do it, because the direct delta, this whole other can of worms, gives us the opportunity to solve these Fourier transformations in a way easier way. But, oh my gosh, I have just been running way too much stuff I had gathered up. But out of all that stuff that I just ran through, what would be the number one question?
Were you able to answer your question?
Which, the one about, oh, that's the whole point of the whole thing. Yeah, so the cosmic background radiation. I tried my darndest to find any sort of like audio or wave or like representation of, I'm like, okay, so like the closest thing we have is this picture, which is the picture that was on the picture that's on the presentation on the ad, that picture of the cosmic background radiation with all the red and the blue and all that. That's like the only thing I could really find. I really wish that I could find the wave, because you could definitely, I feel like, Fourier transform it. I'm not super sure what you would get, but as far as like, I don't know, like stuff that's not that, I took some songs, some little chunks of songs, and made a program that could Fourier transform them, if I can see it. Where is it? Something. Number of components, approximation, summation. So if you wanted to take would that really be useful? Number of components. I'm just going to click on it. So if I took a song and I said to one, take one sine wave and tell me which one it most looks like. It started with this one. And the song thing was just a tiny little piece of a song. Let's see if it'll play. I took random pop song. This might be really loud. Oh yeah, that's really loud. I was like, Fourier transform this. I hear my body calling. That's what I said. And I said, do it to one component, and it gave me this. And then I said, okay, now do it to the maximum number of components. If you're wondering why there's a maximum number of components, it's because in computers, you have discrete functions. You don't have continuous functions. And so when it samples something, so a song, it's going to be all these discrete little points making that sine wave. It's not going to be smooth. It's going to be like and in computers, it does a fast Fourier transform when you use a library for something. But it makes it a lot easier so I don't have to do it by hand. But if I transform, and this definitely utilizes the fact that since the Fourier transform is derived as a special case of the Fourier series, it lets you, oh gosh, it is loading slow. It lets you say, okay, what were the components that this thing was made out of? And as soon as it's done loading, I could show you, but yeah, I know that I'm going now 5 minutes over time, aren't I?
So you're feeding in a song right now, right?
Yeah. So
we're
I'm
gonna get some sort of a wave.
yeah. So it'll spit it out in a second. It's just taking a minute because I said to use 44,000 sine waves to recreate it. And so it's going to do a couple things for me. So I told the program, I guess I should be more transparent about this. So I told the program to observe the song. I said, give me the sine wave components and sum them together and show me the wave. And I also said to create an MP3 that lets us hear the sound that's being recreated. And so I think I have one I already did earlier. I said to do it I'm like, let me hear 2,000 sine waves of a function, not a function, sorry, of that song, that clip that I just played. And it tried to reconstruct it, and it sounded like this. So if you remember the one I played a second ago, it kind of sounds like it at that point. It's getting there. And so I said, okay, try 20,000 sine waves and recreate that song for me. And then it went. And you can hear it coming to life. And I'm like, wow, that's awesome. The freaky thing about it is when I first did it, I didn't give it any phase information. And so it's recreating it irregardless of phase. So it's just slapping the cosines and sines together without any sort of x plus or minus any amount to shift the signs into their exact conformation. I can't believe this is taking so long. Thank goodness I like.
Big ask, right?
It was a big ask. And so I did it, I wonder if I have the list. Oh, this one's only 2. So when I've done it before, so this is from when I did 2 components and it gave me the first 2. But when I do 2,000, it's going to generate this list with 2,000 sine or cosine waves, and it's going to tell me if I add them all together, it's going to recreate that song. And so in the computer world, I can only do it up to, for a 2-second clip, I can do it up to 88.2 thousand sine waves, because that's per second. There's a sampling frequency of 44.1 thousand. And so if I try to go beyond that, there's a limit, and it's like a mathematical limit that says you can't go any farther than that. But at that point, it actually sounds pretty much just like the song, I think. Let's see, is this the one? Nope.
So when you were talking about making these combination waves using sine and cosine, but then you're saying when you're approximating this song clip that the program is just using sine waves, is it sliding some of those sine waves over to imitate cosine? Like if you slide a sine wave over by
I think it's using cosine, and I don't know. That's built into the library, that whether it uses sine or cosine, and so I'm trying to figure out why it prefers cosine, or if it's just the program says just use cosine, it's easier that way. And so it just assumes even if it's shifted and looks just like a sine, it's still defined as a cosine shifted by 90 degrees. And so when it's breaking it down and like doing like all those components, yeah, it spits them all as cosines, because I generated this list up to like, I think it was, did it load? I generated this list up to, however, maybe that's why it's not working, it's because I had this open. But, here we go. So this is in phase. This is using the phase information so that it is preserved. That's why it's not symmetrical. But this is using 20,000 sine waves to recreate that audio clip, which is being turned into a psi of x, more or less. And so if we look at it, that's it zoomed in. Yeah, it's 20,000 sine waves just added together in such a way that you get the exact audio clip that you started with, basically. And so if we wanted to hear it, if you want to say, no way, James, like that's not, you can't recreate that, then let's see, is this it? I hear my body calling. So that's not the original song. That is just that's what the sum of 20,000 sine waves pushed through that equation sounds like. And so the program's it's just playing back the waveform that it generated. But
So if you get the waveform of that cosmic background.
Yeah, so that's what I'm like, man, like I want to get that the some sort of wave out of that. And I've tried all kinds of ways of doing it. One way I tried to do it was I tried pixelating the picture of the cosmic background radiation, so I could actually look at the heat map and somehow convert that into waves. That seemed more like a creative decision than like a scientific thing. But let's see, did it update this list? Yeah, it did. There we go. So that's, if you wanted to know every single component, you could get it by just walking backwards a little bit from the Fourier transformation back to when, in its younger days as the Fourier series, it has inside of itself the ability to spit out every single one of those components if you wanted to know them. So every single one of these, it's going to be 2 pi times that. 2 pi times 1.5 times 2 times 2.5, all the way up to 9,000 whatever. So it's just going to get smaller and smaller and smaller. That's the phase on the right, which is contained in the Fourier transform. Since the Fourier transformation is working in complex numbers, the complex components always tracking the polarity, or the phase. And then the magnitude's just tracking, the height of these cosine and sine waves, because some of them are a larger contributor, and so it gets a larger magnitude.
Well, some people might have to wrap things up. I have a million questions. Does anybody have?
What are the units to measure the axes on the graph? Like I figured the 0 to 2 is probably the seconds.
Yeah, 0 to 2 on the graph that I just had up, which I might even be able to just bring it right back up, because the first, yeah, there it is. So that's 2 seconds. It was a 2-second clip, and so this is the summation of the cosine waves over 2 seconds.
Where's your y-axis?
What is the y-axis?
Yeah.
So the y-axis, whether you're in space, so if we're dealing with space or time waves, a space wave function or a frequency wave function, regardless of which one you're using, the thing that's changing is actually the x-axis. So in the frequency world, which would be your psi of k, you're going to have frequency on the bottom, and it's just going to be just magnitude. And then if you're in psi of x, you're in the time domain kind of land. And so at that point, you're looking at time on the x-axis, and then up and down it's still magnitude. So the y-axis isn't going to change, but depending on whether you're looking at the psi of x or the psi of k, your x-axis is going to change from being time, in seconds presumably, to frequency in hertz. But trying to think of, yeah.
I missed the first 10 minutes, but I was wondering, it looks like you have your wave function, like you mentioned, kind of towards the end, you have one in a wave function form, and you have the other one in an exponent, like an E exponent form.
Mm.
But which one does a computer use? Like, how does a computer best understand it?
So the computer's using an algorithm called the fast Fourier Transformation, and so the computer's doing it instead of, at one point I went from a sum, taking the limit of r to infinity. R would just be the radius of the circle, because we're wrapping these cosine waves around a circle when we're doing this, and we're looking for a center of mass. But with the exponentials, when the computer does the fast Fourier transform, I think it's going back to being a sum so that it can take discrete points as the nth harmonic of each cosine and sine. And so that way, when you're looking at discrete points versus a continuous function, the computer has a way better time just summing up these like matrix or array values, basically. And so the computer, they say the fast Fourier transform algorithm's like the most useful algorithm ever conceived, and they say all this crazy stuff about it. I didn't do too much research on it. I wish that I had.
I'm sure you will.
I mean, this whole thing, like, it really just, I was like, man, like, there's so much ground. There was so much ground to cover, like, just being able to frickin' put in a function and, like, get an answer that's not 16 terms of, like, radicals. And so that was, like, so much of the work just to begin with. And I think, I guess I can show you this one last thing. This will take 2 seconds. So before I figured out the polarity, this is my handy dandy Ableton. Before I lined up the sines and cosines, and this is kind of me hinting at the next thing that I'm going to try to do or figure out. When I had this one, which I hope this isn't super loud. So that one that like loosely resembles it because the phase information isn't being held, but it still sounds like this doesn't sound like palindromic at all, right? Like you can hear their voice, right? What do you think's going to happen if I reverse this?
It'll sound the same.
Let's see. Oh, that's weird. It didn't reverse. Let me try that again. Oh no, it totally did reverse. So yeah, as you can see, it sounds exactly the same forward and backwards. And so I think there's something interesting about that. The fact that something can sound like it's only going in one direction, but it's actually going in both, because it's averaging the summation of cosines and sines without respect to phase. It's like averaging out how something sounds forward and backwards. So imagine me saying, hey, how's it going? And then reversing it, and you're like, oh, it's going to sound like blah, 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 blah. But imagine playing it backwards and hey, how's it going? That would be terrifying. And that's what happened. And that's what happened to me, because I was using voices and stuff, and I reversed it, and it sounded like they were speaking forward still, because it has the ability to average out how something would sound most forward in both directions. And I can't find a whole lot of information on what's going on there. And so
Are you sure that AI isn't creeping in and saying, yeah, this is
Oh my gosh. But I don't know. Maybe there's nothing to it. Maybe I have no idea if it's going to be a big deal or not. But I think it would be interesting if there's some underlying fundamental law of the universe hidden in this, the same way that the uncertainty principle is hidden in it, because whether or not you're putting in a lot of frequency information or a lot of dynamic information, there's like an upper limit for what you can do. So I wonder what the upper limit of how much something can like appear to be going forwards even though it's going in reverse. I wonder if there's some weird thing with that. And it also made me like question like, why do we even perceive time as moving forward to begin with? Like there's not really any like why. So we'll see. But thank you so much for coming. Thank you for thank you for bearing through my attempt at deriving.
So James, you've learned almost none of this in a classroom. Is that right?
No.
You said you remembered the integral, like that trick, but
yeah.
some things you stumbled upon, like Fourier transforms, with the Dirac delta function, you'll encounter that in 256 here. Like you'll get a glimpse of it.
Okay.
You'll do Laplace transforms in that class. It's a different kind of transform, but Euler's formula, eigenvectors. Have you taken linear algebra? And
I'm hoping this was good at preparing me.
Principle, the sine C function. You just stumbled upon all of these classic tools.
Yeah.
Because you're like, I want to know the answer to something.
Yeah.
That's really impressive, and you still do well in school.